Fine. Let's start. Number 10. Augustine's question. There's a question you probably asked when you were a kid and then stopped asking because nobody could answer it. What was there before the universe? Not before the planets, not before the stars. Before everything. Before the Big Bang. Before the beginning. And here's the strange part. The first person to give a really good answer to that question wasn't a physicist with a telescope. It was a monk in North Africa, writing by candlelight, more than 1,600 years ago. Around the year 397, a man named Augustine of Hippo sat down to write a book called the Confessions, and in the 11th chapter, he got stuck on exactly this problem. The popular version of the question in his day was a little cheekier. People like to ask, what was God doing before he made the universe? What was he waiting around for? Augustine could have dodged it. Instead, he did something that still feels modern today. He said the question itself was broken. There was no before, because before is a word about time. And time, he argued, is part of the universe. It was created along with everything else. God didn't build the world inside of time, like setting a model ship into a bottle that was already there. He made the bottle too. He made time itself. And so, Augustine wrote, there was no then when there was no time. Let that sit for a second. Asking what happened before time is like asking what's north of the North Pole. The words are all real. The sentence is grammatically fine. It just doesn't point at anything. Now here's why this matters for us. Fast forward about 1,500 years. Einstein comes along with general relativity, and he tells us that time isn't a stage that events happen on. Time is part of the fabric. It's woven into the universe, stitched together with space into a single thing. And when you run the standard Big Bang model all the way back, time itself begins. There's a moment we label time zero, and asking for a moment before it is mathematically asking for nothing. A theologian writing before the fall of Rome and a physicist with the most successful theory of gravity ever written looked at the same question across 15 centuries and gave almost the same answer. There was no before. The question is the mistake, which would be a tidy place to end the video, except for one inconvenient detail. A lot of very serious physicists think that answer is too easy, and they've spent careers trying to find out what's really hiding behind that word, before. So Augustine gave us the door. For the rest of this list, we're going to open it. Number 9. Time reborn. Most of the theories on this list are going to try to convince you that time isn't real, that it's a trick, an illusion, a kind of cosmic special effect. So before we go down that road, it's only fair to meet the man standing in the doorway, with his arms crossed, telling everyone they've got it exactly backwards. His name is Lee Smolin. He's a theoretical physicist, one of the founders of a whole approach to quantum gravity. And in 2013, he wrote a book called Time Reborn. And the argument in it is genuinely radical, because it's aimed at his own profession. Smolin says physics has fallen in love with its own mathematics. When you write the laws of physics down as equations, time tends to disappear into them. It becomes just another coordinate, another axis on a graph, no different from left or right. And from inside that math, the whole history of the universe looks like it already exists, all at once, past and future laid out like a finished film. Physicists got so comfortable with that picture that they started saying the flow of time, the feeling that right now is real and the future hasn't happened yet, is an illusion. And Smolin's response is, essentially, you've confused the map for the territory. The equations are timeless because you built them that way. That doesn't mean reality is. He flips the whole thing over. Time, he says, is the most real thing there is. The present moment isn't a trick your brain plays. It's the deepest clue we have about what the universe actually is. And then he goes further, which is where it gets wild. He suggests the laws of physics themselves might not be fixed. They might evolve, change, have a history. Most of us were taught that the laws of nature are eternal, that they were the same a billion years before Earth existed, and they'll be the same a billion years after. Smolin says maybe not. Maybe the laws grow and settle over time, the way habits do. And if that's true, then the answer to what was before the Big Bang is almost refreshingly simple. There was a before. Time was ticking. Something happened, and then the Big Bang happened after it. In sequence, in order, just like everything else. Now, Smolin is in the minority here. Most physicists line up behind Einstein and the block universe. The idea that all of time exists together. But keep Smolin in the back of your mind as we go. Because every single theory after this one is going to try to dissolve time, freeze it, or explain it away. And there's at least one brilliant person insisting the emperor has no clothes. Sometimes the loneliest voice in the room is the one that turns out to be right. Number 8, the past hypothesis. Here's something that should bother you more than it does. The basic laws of physics don't care about the direction of time. I mean that almost literally. If you write down the equations for two billiard balls colliding, or for atoms bouncing around in a gas, the math works perfectly, whether you run the clock forwards or backwards. Play the movie in reverse, and every collision still obeys every law. At the level of particles, there is no arrow. There's no built-in sense of earlier and later. The universe, down in its bones, is symmetric. But your life is not symmetric. You remember the past, not the future. Eggs break, they don't unbreak. Coffee cools down. It doesn't spontaneously reheat by stealing warmth from the room. Smoke spreads out. It never gathers itself back into a tidy little stream. Everywhere you look, time has a direction. So where does that direction come from if the laws don't have it? The leading answer has a wonderfully dramatic name. It's called the past hypothesis. And it was sharpened by the philosopher David Albert around the year 2000, building on ideas going back to the physicist Ludwig Boltzmann. The idea is this. The reason time runs one way is that the universe started in an incredibly special state, a state of extraordinarily low entropy. Very ordered, very smooth, very, very unlikely. And ever since, the universe has been doing the only thing it can do. It's been spreading out, getting messier, drifting away from that improbable, pristine beginning toward disorder. That drift is time, the arrow you feel, the one that points from birth toward death, from intact to broken, isn't written into the deep laws of physics at all. It's a kind of momentum, an inheritance handed down from a freakishly orderly first moment. Run everything back far enough, and you reach a state so ordered it's almost suspicious. And here's the part that connects to our actual question. If the arrow of time is just the universe falling away from a low entropy beginning, then what was before might be a state with no arrow at all, no direction. A condition where earlier and later don't mean anything because nothing is flowing anywhere. The physicist Sean Carroll has explored models where time is actually symmetric around that boundary, where the arrow points one way on our side and the opposite way on the other side, like a mountain ridge with two valleys. So what came before time as you know it? Maybe a place where time had no preference, where the future and the past were interchangeable, where the whole notion of going somewhere simply switched off. Now, the honest physicist has to admit the obvious problem. Nobody knows why the universe started in such a ridiculously ordered state in the first place. The past hypothesis tells you where the arrow comes from. It does not tell you why the bow was drawn. We've explained the river by pointing at the waterfall and quietly walked past the question of who filled the lake. Number 7. Two-time physics. So far, we've been arguing about whether time is real and where its direction comes from. But every single one of those arguments quietly assumes one thing: that there's one time, a single line, one thread running from the past, through now, into the future. A physicist named Itzhak Bars at the University of Southern California has spent decades poking at that assumption, and his question is simple and a little dizzying. What if there's more than one? This is called two-time physics. And before your eyes glaze over, stay with me, because the motivation is actually elegant. Bars noticed that a lot of the equations of physics look cleaner, more symmetric, more unified if you write them down in a universe that has not 3 dimensions of space and 1 of time, but 4 dimensions of space and 2 of time. A 4+2 world instead of a 3+1 world. Now your immediate reaction is, that's absurd. I don't see 2 times, I see 1. And that's exactly the clever part. In Bars's framework, there's a hidden symmetry, a kind of mathematical redundancy, that takes that bigger 4+2 world and projects it down into the ordinary 3+1 world we actually experience. The second time dimension doesn't show up as some weird extra clock on your wall. It's folded away, hidden by the symmetry, leaving behind just the single time we know. Think of it like a shadow. A 3-dimensional object can cast a flat 2-dimensional shadow on the wall. If all you ever saw was the shadow, you'd swear the world was flat. You'd build your whole physics around flatness, and you'd be describing something real, but you'd be missing a whole dimension that was there the entire time, just hidden by the angle you were looking from. Bars's claim is that our single timeline might be a shadow like that, a flattened out projection of a richer structure with 2 times in it. And he argues that when you look at the world the 2-time way, some of the deepest mysteries in physics start to look less mysterious. Things that seem like separate phenomena in our world turn out to be the same thing, seen from different angles in the bigger space. So what does this do to our question? It detonates it. What was before? Assumes time is a line you can walk backwards along until you hit the start. But if time is really 2-dimensional, then before is like asking what's to the left of a point on a sheet of paper without specifying which direction left even is. The single backward arrow we keep reaching for might be a human oversimplification of something with far more room to move. I'll be straight with you. Extra time dimensions are dangerous territory in physics. They usually create paradoxes, causes that come after their effects, probabilities that come out negative, the kind of nonsense that gets a theory thrown out. Bars's whole achievement is building the symmetry carefully enough to avoid those traps. It's a niche idea. It's not confirmed, but it's a serious, published, decades-long body of work from a real physicist, and it leaves you with a thought that's hard to shake. Maybe the reason before feels so confusing is that we've been trying to walk backwards down a road when the truth was a whole open field. Number 6, the Janus point. Picture the Big Bang. Whatever image just came to mind, it's almost certainly a beginning, a starting line, the leftmost edge of a timeline, with everything that ever happens stretching off to the right. A physicist named Julian Barber wants you to throw that picture away. In his 2020 book, The Janus Point, he argues the Big Bang wasn't the start of anything. It was the middle. The name comes from Janus, the old Roman god with 2 faces, one looking forward and one looking back. He was the god of doorways, of beginnings and endings, the reason we call the first month January. And Barber uses him because his version of the Big Bang has 2 faces too. Here's the idea. Barber studies the universe in terms of its shape and its complexity rather than its size. And he points out that if you take any system of particles flying apart under gravity, there's always one special moment, one instant when everything is at its most compact, its most uniform, its point of lowest complexity. Pass through that moment, and complexity starts growing again on the other side. He calls that special moment the Janus point, and his claim is that our Big Bang is exactly that, a point of minimum complexity, and crucially, time flows away from it in both directions. Sit with what that means. On our side of the Janus point, the universe expands, structure forms, galaxies condense, planets cool, life appears, and we look back toward the Janus point and call it our past, our beginning. But on the other side, there's another universe, running the opposite way. Its complexity is also growing, away from the same central pinch. And the inhabitants of that universe, if there are any, would look back toward the very same Janus point and call it their beginning too. Two universes, one shared moment, each one calling the other its distant past. So when you ask, what was before the Big Bang? Barber's answer is almost poetic. There was a whole other cosmos, a mirror world, unfolding in the other direction, and from its point of view, we are the thing that came before. Before and after aren't absolute. They depend on which face of Janus you're standing on. And there's a second twist tucked inside this. Most physicists tie the arrow of time to entropy, to growing disorder, the stuff we just talked about in the past hypothesis. Barber disagrees. He thinks the direction of time comes not from growing disorder, but from growing structure, growing complexity. The appearance of more interesting, more organized things, like solar systems, and chemistry, and you. In his picture, time's arrow points toward richness, not decay, which is a strangely hopeful idea coming from a man rewriting the beginning of the universe. Now, this is a minority view. Most physicists still bet on entropy, but Barber's been chipping away at the foundations of time longer than almost anyone alive, and he's earned the right to ask the unsettling question. What if the beginning was never an edge at all? What if it was a hinge? Number 5. The thermal time hypothesis. Let me ask you something. What is a clock actually measuring? The easy answer is, it measures time. But that's a little circular. Look closer at any clock, and what you actually find is stuff moving. A pendulum swinging. A quartz crystal vibrating. Atoms in a cesium atom buzzing back and forth. A clock doesn't sense some invisible river called time flowing past it. It just counts physical changes, and we agree to call that counting time. The physicist Carlo Rovelli took that observation and ran somewhere genuinely strange with it. Starting in 1993, and then in 1994, with the mathematician Alain Connes, he proposed something called the thermal time hypothesis. And the core of it is this. Time is not fundamental. Time emerges from heat, and more shockingly, from our own ignorance. Here's the thread to pull. Imagine a gas in a room. To truly describe it completely, you'd need to know the exact position and speed of every single molecule, trillions upon trillions of them. Nobody can do that. So instead, we describe the gas with a few rough averages: temperature, pressure, density. We blur all those molecules together into a smeared out statistical picture. We do that because we don't know the details, because we're ignorant of the microscopic truth. Rovelli and Connes proved something remarkable. That very act of blurring, that statistical thermal description born from our ignorance, naturally singles out a direction of flow, a flow that behaves exactly like time. The math comes from a deep corner of pure mathematics called modular theory, but the punchline is almost philosophical. The flow of time might be a side effect of not knowing everything. Let that land. In this picture, time is not out there in the universe, ticking away on its own. Time is what a limited observer experiences, because they can only see the average, not the detail. A being who could see every particle, every position, every motion, perfectly and completely, might not experience any flow of time at all. For that being, the universe would just be static, complete, no before, no after, no passage, just a frozen total picture. We experience time in this view because we're squinting, because reality is too fine-grained for us, and the blur we see in its place comes with a current built in. Rovelli later wrote a beautiful little book about all this called The Order of Time, where he puts it more gently. He says the difference between past and future, the whole flowing, moving quality of time that feels so absolute, might exist only because of our blurred, fuzzy, incomplete view of the world. Sharpen the view enough, and time fades out. So what was before time? In the thermal time hypothesis, that's almost the wrong question again. Before there was heat, before there were systems too complex to fully know, before there were observers squinting at averages, there was no flow at all. Time isn't something that started. It's something that appears, locally, wherever the universe gets too complicated to see all at once. Number 4. Causal set theory. We tend to imagine space-time as smooth, continuous. You can zoom in forever, slice any distance in half, then half again, down and down with no bottom. Time, in particular, feels like a smooth-flowing liquid, infinitely divisible, never breaking into pieces. Causal set theory says, no. At the very bottom, reality is grainy, pixelated, made of indivisible atoms of space-time, individual events, and there is a smallest piece below which you cannot go. This idea was developed mainly by the physicist Raphael Sorkin and his collaborators, and what makes it beautiful is how little it assumes. A causal set is just two things: a collection of these space-time atoms, these basic events, and one single relation between them. Which event comes before which? That's it. No smooth background, no pre-existing stage, just events, and the order they're in. Out of that bare skeleton, Sorkin argues, all of space-time, all the smoothness we experience, is supposed to emerge. But here's the version of the theory that's relevant to us, and it's gorgeous. In one model, called sequential growth, these atoms of space-time aren't all just sitting there. They get born, one at a time. The universe grows by adding new events, one after another, each one slotting into place after the events that came before it. And in this picture, the passage of time isn't some external clock ticking over a fixed universe. The passage of time, literally, is the universe getting bigger. Reality is being counted into existence, one atom at a time, and that counting is time itself. The physicist Faye Dowker describes this as a growing block universe. The past is real and fixed, a solid block of events that have already happened. The future doesn't exist yet, not as anything, and the present is the growing edge, the place where new atoms of space-time are constantly coming into being, adding themselves to the block. Time isn't passing over the universe. The universe is accumulating. Now apply this to our question, and you get maybe the most literal answer on this entire list. What was before the first atom of space-time? Nothing. And I mean that precisely in the mathematical sense. Before the first event, there is the empty set, 0 atoms. Nothing to put in order, because there's nothing there. No before, because before is a relationship between events, and there were no events yet to be in a relationship. It's not that there was a dark, empty room waiting for the universe to appear. There wasn't even a room. There wasn't even emptiness, because emptiness is still a place, and there was no place. Just the absence of any event whatsoever. And then, the first one. The first tick. The first atom of everything, with nothing behind it to call its past. Number 3. The no boundary proposal. Now we come to an idea from Stephen Hawking, and it might be the most quietly mind-bending one yet. Because it doesn't say time started with a bang. It says the question of a starting point gently, smoothly dissolves. In 1983, Hawking, working with the physicist James Hartley, proposed what's called the no-boundary proposal. And to understand it, you have to meet a strange tool called imaginary time. In our normal experience, time and space feel completely different. You can walk back and forth in space, but you can only go forward in time. Hawking's insight, borrowing from the mathematics, was this. As you go back toward the very beginning of the universe, time starts behaving less like time and more like space. The hard line between them softens. And right at the beginning, time becomes, in effect, just another direction of space. This is what physicists mean by imaginary time, and it isn't science fiction. It's a specific mathematical move that smooths out what would otherwise be a brutal, infinitely sharp starting point. And when you do that, something elegant happens to the shape of the beginning. Instead of the universe starting at a single, jagged point, a singularity where the math screams and breaks, the beginning gets rounded off, smoothed, capped, like the bottom of a sphere. And that's where Hawking's famous image comes in, the one you might have heard before. Think about the surface of the Earth. Start anywhere and walk south. Keep going. Eventually, you reach the South Pole. And now ask, what's south of the South Pole? The answer isn't some hidden, mysterious place. The answer is that the question stops making sense. There is no south of the South Pole. You've reached the place where that direction simply runs out. Not blocked by a wall. Just done. Hawking said the beginning of time is exactly like that. Travel back toward the Big Bang, and you reach a kind of South Pole of time. Ask what came before, and you're asking what's south of the South Pole. The words run out. Not because something is hiding the answer, but because before has reached the edge of where it means anything. And here's the elegant part. There's no boundary, no wall, no edge, no first instant where the universe abruptly switched on. The surface of the Earth is finite. You can measure it, but it has no edge you can fall off. Hawking's universe is the same, finite in its past, but with no first moment, no boundary, nothing before, because there's no before to have. It's a strangely peaceful picture of the beginning. We imagine the Big Bang as violence, as an explosion, as the most dramatic event possible. Hawking's beginning is the opposite. It's smooth, seamless, rounded. A place where time quietly curves into space, and the whole notion of a starting line melts away. I should tell you this is still debated. Imaginary time is a mathematical device, and physicists argue about how literally to take it. A few years ago, some researchers argued the whole calculation might be unstable when you do it carefully, and others pushed back hard. It's live, contested, unsettled science. But as an answer to our question, it's unforgettable. What was before time? You're standing at the South Pole, pointing south, asking what's that way? And the universe is gently telling you, there is no that way. You've already arrived. Number 2, time from entanglement. Everything we've talked about so far has been theory. Beautiful theory, serious theory, but ideas on paper, equations and arguments, and thought experiments. This next one is different, because in 2013, somebody built it on a table, in a lab. They made a frozen universe and watched time appear inside it. Let me back up. In 1983, two physicists, Don Page and William Wooters, were wrestling with that timeless equation we'll get to in a moment, the one for the whole universe that has no time in it. And they came up with a way out that is so strange it sounds like a riddle. Time, they said, could come from entanglement. Entanglement is that famous spooky link between quantum particles, where two particles become so deeply connected that you can't describe one without the other. Page and Wooters had this idea. Take the universe and split it into two parts. Call one part the clock and the other part everything else. Now, entangle them. Here's the riddle. From the outside, looking at the whole system, the clock, and everything else together, nothing changes. The total state is frozen, static, timeless. If you could somehow stand outside the entire universe and look at it, you would see no motion at all, a perfect, eternal, unchanging block. But, and this is everything, if you're inside, if you are part of everything else, and you check yourself against the clock, comparing your state to the clock's state, then you see change. You see the clock ticking. You see things evolving. You experience time passing, vividly, undeniably. Same universe, from outside, frozen forever. From inside, time flowing. The difference isn't in the universe. It's in whether you're looking at the whole thing, or looking from within it. For 30 years, that was a gorgeous idea, with no way to test it. And then, a team led by Ekaterina Moreva did the experiment. They took two photons, two particles of light, and entangled them. One photon they used as the clock. The other was the system, the little toy universe. And then they looked at it two ways. When they played the role of the internal observer, measuring the system against the clock photon, they saw the system evolving, changing, behaving exactly as if time were passing. Time was real, from the inside. But when they played the external observer, measuring only the global properties of the whole entangled pair, treating it as one closed system, they could demonstrate that nothing was happening at all. The state was static, frozen, timeless. They built both at once, a universe that is frozen from the outside and alive with time on the inside. The exact thing Page and Wooters dreamed up in 1983, sitting on an optics bench made of light. So, what does this say about before? It says that time might not be a fundamental feature of the universe at all. It might be a relationship, a correlation between you and a clock, both stuck inside the same frozen hole. And if time is something that only exists from the inside, for observers entangled with a clock, then before the universe is a phrase spoken from a place where there were no observers, no clocks, no correlations. From the outside, there is no time, so there is no before. There's just the frozen everything, complete and entire, with time blooming only for those of us caught inside it. Number 1. The timeless universe. We've arrived at the deepest one, the idea that sits underneath almost everything else we've talked about. And it comes from a single equation written down in 1967 by two physicists, John Wheeler and Bryce DeWitt. They were after the biggest prize in physics. They wanted to combine Einstein's gravity with quantum mechanics, the physics of the very large with the physics of the very small, and write a single equation that describes the quantum state of the entire universe. Everything. All at once. One equation for reality itself. They did it. They wrote it down. It's called the Wheeler-DeWitt equation. And when they looked at what they'd written, they found something that has haunted physics ever since. There's no time in it. I want to be precise about how strange this is. The central equation of ordinary quantum mechanics, the Schrödinger equation, has time right there in it. It describes how things change from one moment to the next. It's a machine for turning now into later. But the Wheeler-DeWitt equation, the one for the whole universe, has no such term. No later. The equation describes a wave function for the entire cosmos that simply does not evolve. It just is. Static. Frozen. Eternal. Taken at face value, the most fundamental description of everything that exists says that nothing ever happens. The universe doesn't unfold. It doesn't move. It doesn't go from past to future. Because at the deepest level, there is no past and no future. There's just the whole of reality, sitting there, complete and motionless, like a single photograph that contains everything that ever was and ever will be. Physicists call this the problem of time. And notice the word, problem. Most of them don't want this to be true. They look at that missing time and they say, the equation must be incomplete. We must be misunderstanding something. Surely time has to come back somehow. And a lot of clever work goes into recovering time from the equation, showing how the flowing time we experience could emerge as an approximation, under special conditions, for observers like us. Which, you'll notice, is exactly what almost every other theory on this list has been trying to do. Page and Wooters, with entanglement. Ravelli, with heat and ignorance. They're all trying to explain how time appears inside a universe whose deepest equation doesn't contain any. But there's another way to read it. Maybe the equation isn't broken. Maybe it's telling the truth. Maybe the universe really is, at its foundation, a timeless thing. And everything we call change, every sunrise, every heartbeat, every memory, the entire experience of living through a sequence of moments is something that exists only from a particular point of view, from inside. The motion is real to us, the way the motion in a film is real to you while you're watching it, even though the whole reel exists all at once, every frame already there, nothing actually moving on the strip. And if that's right, then this whole video has been chasing a ghost. What was before time? There was no before, not because time had a tidy little starting line, but because time was never the fundamental thing in the first place. There is no before the universe. For the same reason, there's no scene before the first frame of a movie that simply exists, all at once, in a canister on a shelf. The before isn't hidden. It isn't lost. It was never a real place. It's a question your time-bound mind can't help but ask, about a reality that was never bound by time at all. We are creatures who live in the flow. We're built out of memory and anticipation, of was and will be. So of course we look at the beginning and ask what came first. It's the most natural question in the world. But maybe the universe doesn't have a first. Maybe it doesn't have a flow. Maybe, underneath everything, it simply, completely, timelessly is. And we are the part of it that happens to look around and feel the moments going by and wonder what could possibly have come before. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.